And again, thank you for joining this webinar on evaluating the merits of coupled renewable battery systems. My name is Andrew Mills, and I'll be introducing the speaker today and then moderating the question and answer session at the end. Today's speaker and the lead author of this research is Will Gorman. Will Gorman is a graduate student researcher in the Electricity Markets and Policy Department at the Lawrence Berkeley National Laboratory. His research focuses on the economics of distributed energy resources, the integration of variable generation into the electric power system, and hybrid renewable energy systems. Previously, Will worked with the utilities practice at the Brattle Group. Will has a Master's in Science in Energy and Resources from the University of California at Berkeley, and he's currently a PhD candidate in the same department. He also holds a BS in Chemical Engineering from the University of Texas at Austin. Will, go ahead.
Great. Thanks for that introduction, Andrew. And thank you all for joining us today to hear a little bit about the work that we've been doing. Trying to answer the question that you see on this slide, are coupled renewable battery power plants more valuable than independently sited installations? And so a free copy of that report can be found at the link, again, that Andrew mentioned that's on this slide. The slides themselves, I don't think are yet posted. And so this work was funded by the US Department of Energy. And it's a team effort for sure. So Andrew, obviously, as a co-author and collaborator, but the team was also made up of Christina Crespo-Montañez, James Kim, Dev Milstein, and Ryan Weiser. So before jumping in, just a little bit of a roadmap of where we'll be going today. So I'm going to introduce and motivate the work that we've been doing on hybrid renewable storage systems over the last few years. Then I'll talk specifically about some of the economic valuation methods that are central to answering the specific question that I introduced on the slide before. I'll then dive into those results and try to answer that question as best as we could with this analysis. And then I'll conclude with some of the key takeaways that we want you to have. And then I'll summarize a little bit of where our research is headed at LBNL over the months and years to come. So introduction, motivation. I think probably for many people on this call, in this webinar, I think it's going to be no surprise that there have been increased findings that integrating growing levels of variable renewable energy, so specifically wind and solar, may require and will require strategies that enhance grid system flexibility. And storage technologies are one of the kind of suite of options that can be used to enhance that flexibility. And due to their declining cost, in particular over the last 5 to 10 years, really, batteries have become kind of the technology du jour, the popular choice for thinking about some of this flexibility. But the siting decision has been somewhat of an interesting and unexpected development over the last few years. And that siting decision is that the developers have shown an increased interest in co-locating the generation, so wind and solar plants, with batteries at the point of interconnection rather than siting them separately. And there's many considerations that siting choice kind of contains that developers will consider. And we're not going to be able to kind of get to all of those in this report, in this research. But we will get to a few, and that siting choice does impact effective renewable integration, depending on the different transmission constraints that the system has. And so it's important to tease out, what is the trend, or why are we seeing this co-location, so that we can understand this potential renewable integration angle. And so just to drive home this developer interest with a little bit more data and quantification, this is a chart put together by some colleagues at the lab, Mark Bollinger and Joe Rand. And this is work where they've looked at the 37 ISO and utility interconnection queues across the US. So this represents roughly 85% of load in the United States. And you can see here, the common story that solar and wind are really dominating the queues, with a decrease in gas and basically no nuclear, no coal. But what I want to really focus on in the slide are these hatched portions. And these are the portions of those technologies that are choosing to co-locate and these are, again, all proposals, not all this capacity will be built, but you can see how that rise in co-location is pretty dramatic over the last 3 years. For solar in particular, there is a little bit of it for wind, but a significantly smaller percentage. And then it's also interesting to look at the standalone storage section, that third section, where you can see the amount that's being co-located with another resource, and the non-hatched part, which is being cited independently. And so this interest is really what we're trying to, in part, unpack with this research. And so I showed you a US-wide graphic on that prior slide, and so now we can dive into some of the regional trends here, and you can see that CAISO in California and the non-ISO West have the dominant fraction of these proposed plants. So in California, as of the end of 2020, basically 90% of solar projects were being co-located with storage, and that second highest percentage, which is 70%, which is the West, not including California. And you see that other regions in the United States also have decent penetrations. There are these projects being proposed, but they are at a significantly smaller percentage. And then there is significantly less interest in the wind co-location as compared to solar. The last thing I want to kind of draw your attention to is that the percentage of batteries that are choosing to co-locate also has a regional flair, where you see California, almost 65% of batteries are being put in co-location configuration, whereas in New York, you only see 2%, so a significantly smaller fraction. And so some of these regional trends that we've been seeing were things that we wanted to answer in our analysis of the valuation of these coupled projects, and we'll talk about that once we get into the results. I do want to do a little bit of log rolling before jumping into the specific research that we did to answer this coupled versus independent siting question. And that is a paper that we released last year, which was outlining the pros and cons of hybridization more from a qualitative angle. So talking about a lot of the concepts that people might want to think about when they think about this trend towards hybridization. I won't spend any more time on it here, but if you are interested in a little bit more of the conceptual discussion, do encourage you to check out that Electricity Journal article. It's open access, and you can see the title of it below. But the reason I put this slide up is because that was a more qualitative discussion, and we were really interested in quantitatively analyzing what you see in this red box here, which is some of the operational and siting constraints that people might think about if they're seeing a lot of this co-location. And that's what we're trying to quantify in this particular paper. And so that's the conceptual notion that I want to kind of bring home on this slide. And I have somewhat of a provocative question here that our report doesn't necessarily answer, but it's one to think about, and it's part of the framework of this analysis. And is the paradigm shifting on how to site power plants? And so the idea here is that historically, or maybe when you think about the electricity network, that paradigm was we have all these balancing authorities who are going to manage the transmission network, and they optimize a fairly geographically dispersed set of technologies because they have a bunch of transmission lines that they can manage. And so when you think of co-location, that suggests either that conventional wisdom is changing, or maybe it was slightly wrong. And there could be many, many different reasons for that. We've heard a lot about the queues becoming very packed, and so there might be some amount of transmission constraints that are leading to this co-location play. There also could be operational or cost synergies that have led to this co-location strategy by developers. So that the operational synergies could be an ability to capture value that isn't that they wouldn't be able to capture if they were sited independently. And then that cost synergy is just the notion that by putting these projects into one, maybe you can avoid some duplication of costs, whether that's land or different transaction costs that come with developing a power plant. And then the last one, which I think for a lot of people has been the reason why this is honestly happening, is federal incentives. So there's an investment tax credit that storage can only take advantage of if it is co-located and charged at least 75% of the time with a renewable energy asset. And so a lot of people point to that as a reason for this co-location. And so these questions, these issues are things that we wanted to try to quantify as best we could, and then maybe kind of tease out this much broader question about how we kind of operate the system as a whole. And the last introduction motivation slide is just a way to narrow the scope and really hone in on what we are studying here so that we can be as clear as possible, because defining terms is always challenging, and we want to make sure we're very clear here. And so we only consider renewable plus battery hybrids, and that is due to the current commercial interest in these particular applications, as I showed on the prior slides. And so the reason it's important to point this out is because the term hybrid can sometimes be used or is applied to many different types of concepts. Our scope is what you see in a smaller rectangle. We're just looking at wind plus battery and solar plus battery. But hybrid can refer to wind plus solar. It could refer to solar plus a fossil fuel unit. It's often referred as a virtual power plant and aggregated distributed energy resources. Also, the term hybrid in some contexts and with some groups explicitly refers to how you operate these systems in kind of a synergistic way, so that you are bidding that unit as one resource, and that's what people call a full hybrid. So there's a lot of nuances around this term, and we just want to be clear that we're really just looking at this coupling question of solar or wind with a battery. And so just want to be clear, moving forward, I'll probably refer to coupling rather than hybrids, just to be crystal clear about what we're looking at. All right, so next I want to talk about the economic valuation methods we use to answer this question about independent versus coupled economic value in the market. So our analysis focuses on the 7 nodal markets in the United States. And the nice thing about these 7 markets is that they're pretty diverse in their resource mix, and you can see that on the graph on this slide. California has the biggest penetration of solar. You can see that in the CAISO bar as compared to the other regions. But some regions you see have coal, others don't. Some have pretty big portions of nuclear, whereas others don't. And so that's a nice variation that we can bring into our analysis. They all operate day ahead in real-time energy markets, which is important for us because we're going to use both of those when thinking about the value of storage arbitrage. And then the last, probably the most important point and conceptual thing to understand about US markets for this particular research that we're doing here is that they use nodal LMPs, which reflect transmission congestion at a pretty granular state. So, any market in the United States could have thousands of these nodes across their network. And that's fairly unique, at least when compared to some of the European counterparts, which use more zonal pricing schemes. And the reason this is important for what we're doing is that, our question is geospatial in nature. Is there a big constraint to siting that battery at a place where you might want to site a wind or solar plant? And to really answer that question, you want to have a pretty geographically resolved understanding of value. And because the US employs this nodal system, we get access to a pretty granular nodal valuation. And so I'll describe this in a little bit more detail, more explicitly about what we do, but it is an important kind of conceptual point to keep in mind as we go through this. Okay, so how do we calculate the value of these coupled projects? So we develop a pretty standard optimization linear program algorithm, and we assume a price taker strategy. And so what that means is that these resources do not impact marginal prices. So we assume that they can get the marginal price that the market is sharing. So this is very important to considering marginal investment decisions. But the limitation of this type of analysis is that it's hard to look at what projects what's going to happen in the next 50 years as more and more and more storage resources are developed. So it's really a snapshot of the current markets as they exist today. And then we developed 2 algorithms to do this valuation. We have an optimistic algorithm and a pessimistic one. In the optimistic case, we assume that these storage coupled projects can maximize real-time energy market revenue with perfect foresight. So they know what the prices are going to be, they know what the renewable asset is going to produce, and they just maximize profit. Obviously, that's unrealistic for a number of reasons. And so we developed this pessimistic case to bound our valuation. In this case, we allow the storage resource to see day-ahead prices, and you develop the optimal schedule with those day-ahead prices, but you realize revenue in the real-time energy market. And so this is somewhat of an achievable case because day-ahead prices are released ahead of time from the real-time market. So storage assets will know what the day-ahead prices were, and then could choose to operate based on those prices in the real-time market. So we think this is a more realistic or achievable case, but it's pessimistic in that it's not sophisticated. You know, we're not using machine learning algorithms to predict prices and operate in the real-time markets. There probably are more complicated and involved strategies. And so that's why we think these are decent bounds. And then our key inputs here to that optimization is that we have LMP prices at nodes within the utility scale solar, wind, and some high volatility locations. I'll speak a little bit more about how we pick these high volatility nodes a little bit later. And then we do have annual capacity prices across these markets by year, and we allocate the value of those prices to the top 100 net load hours in each market. We have a sensitivity analysis that considers regulation prices at the ISO zonal level. And then we have simulated PV profiles and wind profiles using weather data across the United States. And so those are the key inputs to the optimization. And then the key outputs then are energy, capacity, and regulation revenues. And we levelize those using the generation from VRE. So when we go to the results, you're going to see a bunch of dollar per megawatt hour metrics. So these are all levelization metrics. But it's important to note, even though we are looking at storage, we are only using the megawatt hours of the renewable energy asset production to do this levelization. So it's not some type of storage arbitrage or cycling megawatt hour. It's just levelized using that VRE. So just kind of keep that in mind once we get into those results. And so there are two key metrics that we've developed in this analysis to try to answer some of those regional research questions and then this coupling versus independent siting question. So these next two slides, I'm going to talk about these metrics, and then the results are going to be structured around these metrics. So these are kind of important to hold as we move forward in the presentation. So the first metric we've termed is this storage value adder. And the idea of this metric, it's used to understand the value boost you get from adding a battery to a VRE, so wind or solar, at the same geographic location. So you can see the calculation in the below equation, fairly standard or simple equation, where we take the energy value of a coupled project, the capacity value of a coupled project, and we subtract out the energy value of a standalone wind or solar plant and the capacity value of a standalone wind or solar plant. And that's the storage value adder. It's the additional money that you can make if you added a storage to that same location. And it's particularly helpful, this metric, in understanding the potential for coupled projects to mitigate the value deflation. So there's been a lot of talk about, you know, the more and more solar, the more and more wind that gets installed, it depresses prices at those nodes because they're low marginal cost resources. And so by looking at the value of adding storage, you can see like, well, do these storage assets mitigate that deflation? And it's also a very useful metric to see how regional trends and the regional value of adding a storage asset to your renewable asset differs. And so it gets a little bit at, you know, when we were looking at that table a little bit earlier and we were seeing there is this regional breakdown of interest, this metric can help try to evaluate that metric. Okay, so that's the first one, storage value adder. And then the second metric, which is much more related to the the title of this presentation, our key question of looking at this co-location constraint is what we term here the coupling penalty metric. And this evaluates the constraints involved with co-locating batteries at the same VRE location. So you can see the equation below. It has many of the same attributes of the equation on the prior slide, but we have added here the storage value component. And so what we do here is we have the same kind of standalone VRE asset at a location. We look at the coupling value at that same VRE location. So those are the same terms from the prior slide. But the storage value, importantly, is looking at the highest volatility nodes within a given market. So it's worth to unpack what we do here a little bit. We have all hourly pricing data points for the 50,000 roughly nodes there are across the United States. So what we do there is we calculate a volatility metric of all of those nodes over the last 10 years. And we take the top 30 nodes in each market over those last 10 years, and those become our high volatility nodes. These are nodes that have particular high energy arbitrage value, which I'll show that on one of the results slides. But for now, you just have to take that as given, is that this volatility metric correlates very strongly with the storage value. And so then what we do to calculate the storage value is, instead of looking at the wind and solar nodes, which is where we calculate standalone VRE and its coupling value, wind and solar locations, we're trying to look at, like, well, where on the system is it most valuable to put storage? That could be at a pretty high load location, maybe closer to a city, or close to some industrial process or what have you. And by then adding that into this coupling penalty, we can get a sense of what value is being lost by coupling or adding storage at a wind or solar location. So that's kind of an important conceptual point that I want to illustrate here. But there are additional constraints that this penalty would take into account. And so that's what you see here in the second bullet. So the first one I just walked through is that this reduced geographic option to battery siting. So this is that siting at a wind or solar location versus a high volatility location. But we also look at the constraints that can be applied to these hybrid coupled projects, is that you might have some infrastructure sharing. So you might have an inverter or a point of interconnection limit that is actually smaller than the combined size of your battery and VRE system. So that's an additional constraint that we take into account in this penalty. And then in order to qualify for the investment tax credit, there are also some restrictions on grid charging. And so we are also applying that constraint in this metric, in this framework. Importantly, though, we will have sensitivities where we relax the second and third constraints on this slide and just look at that geographic constraint. And that's going to be one of the key takeaways. So spend a lot of time, on this slide. This is a particularly important point to make because it's kind of central to the methods that we're applying. So again, this is the coupling penalty metric. And this is where we're really looking at the difference between co-location and independent siting. Okay, so this is somewhat of a busy slide, so bear with me. I won't spend too much time here, but there's a number of defined decisions and parameters that we have modeled here. And I just wanted to kind of give that laundry list here for those that are curious. I mentioned some of the geospatial information. We ultimately run our optimization across 1,700 pricing nodes. So these are wind, solar, and high volatility nodes that we've selected. In the slides, then the results section will show results for the following years: 2012, 2014, 2015, 2017, and 2019. We have these two different dispatch algorithms. So we have this perfect foresight, and then we have this day ahead schedule that I mentioned earlier. We have the ability to look at different points of interconnection capacities. So think about, if you have a 100 megawatt solar plant, we look at a point of interconnection at 100 megawatts. And then we look at one where you add the battery capacity to that point of interconnection. The idea here is that if you have more interconnection capacity, you can get more revenue, but it does come at an additional cost. We look at both grid charging and non-grid charging for that coupled project. And then the last three, finally, there is considerations of degradation in our model. We have a fairly simple implementation where we look at a linear penalty. So basically, it's ensuring that there's a certain amount of arbitrage value in a given hour, and it will not cycle the battery if that value isn't reached, but we do vary that penalty different ways. I'm happy to speak about that degradation point in more detail if there's interest. And then we do have the capacity to change the storage size and the storage duration, but as I'll show on the next slide, we are not going to do that for this particular work. So, but I will explain that on the next slide when I'm talking explicitly about the sensitivities, which directly relate to all those design parameters that I just walked through. So 6 main sensitivities that we're going to consider here. The default scenario, so our baseline case, which will be the predominant results that you'll see on the slides, is that we don't consider ancillary services, but we do have sensitivities where regulation reserves will be included in that value. We're going to model a 1.3 ILR AC coupled solar system, but we do have a sensitivity where we look at a 1.7 ILR DC coupled solar system, and this is to take advantage of potential clipping issues that have been one advantage or one positive thing that people have talked about when it comes to these hybrid projects. In a baseline case, we're going to consider a perfect foresight algorithm, but we do have a sensitivity where we use that more pessimistic schedule that uses day ahead prices. We're going to disallow grid charging in the default case, but we will have a sensitivity where we relax that constraint, as I mentioned, and allow that coupled project to charge from the grid. In the baseline case, the fifth scenario, we will have the POI limit at just the renewable energy capacity. So it won't be able to export the renewable and battery producing at peak at the same time in that default scenario. But we have another sensitivity where we increase the POI limit to be the sum total of the max VRE and storage capacity. And then the final sensitivity is we vary the degradation penalty. So this is just sensitivity to see if we restrict cycling to the most valuable times, does that significantly impact our results? And as I just mentioned on the prior slide, we are only going to look at a 4-hour duration battery with a 50% battery to generation ratio. So we don't vary that. So that is some future work that we are looking at to vary, to look a little bit more deeply at these different configuration choices when it comes to the battery size. All right, so that was it's pretty long, pretty detailed methods section. I have about 15 more minutes left as I walk through these results. So if you do have questions, please feel free in this remaining time, put those in the chat. We should have plenty of time to get to those. So the way that I'm going to structure these results is I'm first going to talk about the storage value adder metric. So remember, that was the first metric that was just looking at how much what's the value boost you get from pairing a storage system at a wind or solar location. So we'll talk about that metric first. And then the second half, we'll talk more explicitly about this coupling penalty metric. So again, just to reframe our key questions as we jump into these results, can market revenues explain the higher commercial activity in the Western United States? Can they explain why commercial activity is higher for solar rather than wind? And then the third question, again, the title again of this webinar, does the traditional concept of independent siting of resources not apply to VRE and storage technologies? Okay, so those are the questions to keep in mind as we move through these results. Okay, so this is the storage value adder top line result. So you can see that here in the chart where we have the storage value adder on the y-axis. Again, all of these values are positive because we're not considering a net value calculation. We're not considering costs. We're just looking at the increased market value. So these are going to be positive. And we have solar coupling on the left, and we have wind coupling on the right. So what are some things we want you to take apart from this graph? The first is that there's a particularly high value in CAISO, so the California region, and it began to diverge from other markets in 2015. The second point to kind of take out of these graphs is that prior to 2019, ERCOT, so the Texas region, had a storage value adder that was the lowest of all of the ISOs, but then it jumped in 2019, and that aligns well with, for those of you who are deep into these markets, prior to 2019, in these years that we considered, there wasn't a lot of scarcity pricing. So ERCOT is an energy-only market. They have the potential to have wholesale market prices jump to as high as $9,000 a megawatt hour. That didn't happen too often until 2019, and you can see that the value of storage dramatically increases in that year. And then the last point to see here is that we don't see a significant change in the value adder between solar coupling and wind coupling, besides in CAISO. And we're going to unpack that last point a little bit more on the next slide, where I tease apart kind of the two key drivers of this particular metric. So we're still looking at the storage value adder, so that same metric that we were looking at on the prior slide, but now I'm diving deep into the California and Texas regions. So you see California on the left, Texas on the right. You see the solar and wind that split these graphs, and then further, we split it up by year, and then the bars are split up between standalone VRE on the left and a coupled project on the right. And so what you see here, if we turn your attention to the California, this left figure, is that between 2012 and 2019, the value of standalone solar dramatically decreased. And that correlates very strongly with the rise of solar between those 2 years from 2% to 19% of generation. And so this is the notion of the value decline that can happen in these markets when you have increased penetrations. But what's interesting is that you see that the coupled battery in 2019 almost offsets the value decline. So the value of solar in 2012 was around $50 a megawatt hour. And when you added that battery in the 2012 time period, that value almost gets maintained. And so that's kind of one interesting takeaway. And that is one of the drivers of the storage value adder, which we have in this black number. That's that storage value adder metric that relates to the slide previous. Now, if I turn your attention to Texas, you see it's a different story of why the storage value adder increased in 2019. You can see that the value of solar actually went up in that year. And again, that relates to the fact that scarcity pricing was higher in 2019, and solar in ERCOT has not penetrated as much. And so it can still take advantage. It's producing oftentimes during those scarcity pricing peak time periods. But you see that the storage value adder has jumped from $6 to $21 because the value storage could particularly take advantage of that arbitrage opportunity in Texas, and that dramatically increased the boost. And so you see that that's a somewhat different story than in California, and it goes to this storyline of the penetration of solar. It plays a big part in how much value you're going to get from that coupled project. And I want to remind you that in California, we're seeing almost 90% of all solar projects getting, co-located with storage. And part of that storyline here is likely related to this offsetting of value decline. Drink some water. Okay, great. So we also looked at the results at an individual node level. Sorry, I've lost my voice a little bit. 1 second. Okay, hopefully that will be enough water. So that's what I'm showing here, the individual kind of detailed nodal analysis for solar couples and wind couples. And what you can kind of see if you look at the different shading of these colors in these graphs is that there's not a huge amount of difference at the nodal level in many of the regions. So it's a lot of these color shades, are operating between 2.5 or maybe even $5 megawatt hour difference between the aggregated storage value adder within that market. Now, ERCOT is a notable exception here, and we'll have a little bit more detail of this on some slides that in a few slides. But you can see particularly bolded colors in ERCOT, especially on the solar nodes. And what that just points out is that there's higher volatility in that ERCOT region, where you see the West has substantially higher value to coupling a battery in that region compared to the eastern part of Texas. And so that's just going into this slight difference in what we see in the ERCOT region. Okay, so that was all the storage value adder metric. I'm now going to pivot to talk about the coupling penalty metric. And so just to remind you, because I know there was a lot I talked about when I described this metric originally, what we do here is we take the value of the standalone VRE, we add that to the value of a standalone storage, which is calculated by identifying the 30th most volatile nodes within a given market. And then we subtract out a coupled value project, which has VRE and storage at the same location, but at a wind or solar node. So again, what you see here is that there are significant penalties associated with this co-location. And we didn't find serious divergences between ISOs. So, you know, some ISOs obviously there's a higher penalty than for others, but they're all operating, you know, within the $10 to $20 a megawatt hour penalty. But New York ISO is a notable exception, where we saw the penalty was significantly higher in 2012 and 2015 compared to other markets. And I think it's important to kind of dive into the anecdote here in a little bit more detail, just to give a little more flavor of, you know, what this coupling penalty represents. The highest value, highest volatility nodes in the New York region that we identified were all located in Long Island, or a lot of them were located in the Long Island region, which has some significant transmission constraints into New York City. And so you see particularly high volatility. And there's not also a lot of land for wind or solar in those regions. So there's not a lot of wind and solar nodes there, and you probably couldn't build a lot of wind and solar there. And so that penalty is in part relating to that constraint, is that there's this high volatility location, the New York ISO, that you probably can't site a wind and solar farm here. And so we are trying to quantify that here. And so just to give a little bit more flavor to this nodal value, I have two graphs here. The top graph is describing that correlation that I mentioned a little bit earlier about the annual standard deviation to the storage value. And you can see that there's a really strong correlation between that standard deviation metric, which is how we identify the most valuable nodes in a given market, and then the storage value that they can ultimately get. So as there's more and more volatility, there's more and more storage value opportunity. And then the bottom graph shows the distribution of storage value at the different nodes that we look at in this analysis. So again, we have the high volatility, high value nodes, we have solar nodes, and we have wind nodes. So you'll see that there is a decent amount of overlap actually between all these nodes, but the median value is higher for those high value nodes. And so that is what's going into that coupling penalty. That's why we see that there is a penalty, because by siting things at a wind or solar site and missing out on those high value nodes. But I think, you know, when looking at this chart, I was a little surprised that there is still so much overlap between those high value nodes and the wind and solar nodes. And so this is kind of the last results slide that I'll focus on, and then I'll conclude, and then we'll open it up for questions. You know, if you were hearing me talk in those prior two slides, you know, there is a big coupling penalty that we did find. But I want to remind you that there were a few additional constraints beyond just the geographical constraint that we were looking at. And so this slide is taking a look at those sensitivity cases to see how they affect this penalty. So what you see in this waterfall chart is in this leftmost bar, this is the default case. So This is the case when you average across all of the markets that we were looking at the results on for the prior two slides. We get an average coupling penalty of $12.5 a megawatt hour, so a fairly significant penalty. But then when you look at all these different sensitivity cases, you see that the coupling penalty steadily decreases. So the first sensitivity that I show here is that, well, let's look at a higher POI. So what if we increase the POI to be the same size as the VRE plus battery? That decreases the penalty by roughly $2 a megawatt hour. When you allow grid charging in these coupled projects, that further decreases the penalty by $3 a megawatt hour. In the prior slides, I was showing a sensitivity case where I was actually looking at the highest volatility node over the last 10 years. If we use the 30th highest volatility node, the penalty pretty dramatically decreases by $3.6 a megawatt hour. And that sensitivity is particularly important to think about because, you know, in reality, even though there are these really high volatility nodes out there, it might be quite challenging to identify them. And even if you could identify them, it probably wouldn't be able to absorb a large amount of storage installations because that value would quickly get arbitraged away. So it's worth looking at a point in the distribution that is potentially less volatile. And then finally, the last sensitivity that I show here is when we use the day-ahead schedule. You know, so the pessimistic algorithm rather than the optimistic algorithm, that penalty decreases anymore. And that's because the intuition behind that is because, you know, when you cite things at a high volatility site and you have perfect foresight, you can just maximize that arbitrage value. But when you have a day-ahead schedule, it might be harder to do so. So, you know, when you couple all of these sensitivities to which, you know, I might say is a more realistic penalty calculation, you get that combined number of $1.6 a megawatt hour. So there's still a penalty, but substantially smaller than what we were showing in this default case. And then you can compare that to some back of the envelope calculations that we've done on the potential cost savings that due to coupling, one of which is construction cost savings. So we have heard from developers that there are significant savings, potentially even higher than what we model here, but we've modeled here around the order of $5 a megawatt hour. And then again, I mentioned the value of the investment tax credit, which is $10 megawatt hour when you do this coupling. And so combining those two together, you get about a $15 per megawatt hour cost saving. And that ends up being more valuable than even the coupling penalty. And so the main point of this slide, you know, these are averaged. So obviously there's a lot of nuance if you look at specific markets and specific technologies. But the concept to get across here, and it's one that, you know, going into this, I wasn't necessarily sure we would find, is that, you know, even if you just look at the construction cost savings, there are likely many reasons why you would choose to do this coupling and add on this co-location constraint, because there are significant savings you can get when you build these projects. And so that is an important takeaway to think about and when you think about our results. So I just want to conclude and have hopefully 15 minutes of questions. So quickly, commercial interest in coupled projects differs from the convention of independently siting and operating electricity facilities via balancing authorities. That was this conceptual point that we made in the introduction. And then in our results, we found that coupled projects can significantly boost standalone VRE value across all markets of the US. So that value boost ranges from $5 to $16 a megawatt hour, depending on the sensitivity case. And we did find that the biggest boost was in California, a place where there's the highest penetration of solar to date. And so coupled projects can oftentimes offset that value deflation. And then lastly, we did find a penalty to restricting the location of that storage asset to a wind or solar node. We found that coupling penalty ranged from $1 to $12 a megawatt hour, depending on the sensitivity case. And I think that it really should drive home the point that future siting decisions, now that we are living in a world with more and more storage, will need to consider this nodal volatility more deeply. And obviously developers are considering this. but we have found that that does significantly affect the valuation of these projects. But even though there is this coupling penalty that we found, the value of both the investment tax credit and project development cost reductions should very well offset this penalty. And so we see, a future likely involving both these hybrid coupled projects as well as independent battery siting. So with that, I will conclude the presentation. I have emails up here for both myself and Andrew if you want to reach out to us. But now let's go ahead and jump into the Q&A portion.
Great. Thanks so much, Will. We'll start off with just a couple of things to clarify the scope of this. A couple of questions came in around, did we see any differences in trends on hybridization between things like utility scale projects versus community scale or private behind the meter installations? And along those lines, just asking a lot of questions about whether or not we included any sort of behind the meter factors like net zero export or self-consumption.
Yeah, so all good questions. It's important to clarify this point. Yeah, so our scope was purely on utility scale applications. So those wind and solar locations were all projects greater than, or actual installed projects greater than 1 megawatt. So pretty large solar and wind projects. And those nodal locations were, again, in the transmission network. So the short answer is no. We didn't look at behind the meter or community scale applications. Our work, and conceptually it could still be applied, given that some of those high volatility locations could be located near to load regions, which would then have implications for behind the meter applications. But that isn't something that was really the focus of what we did. We didn't spend a lot of time doing a geographic analysis of those high volatility locations. So you shouldn't think about any of this work really in the context of that behind the meter question, but really just utility scale projects.
And then I'll just have a couple of questions on the methods before we sort of move into questions that are more on discussion of the results. So first on the methods, why is it that the capacity price was allocated to the top 100 net load hours instead of crediting hybrids on a $1 per megawatt day basis? Was this to do a consistent analysis in the different areas that have or don't have capacity markets?
Yeah, no, so it's a great question. It is somewhat due to that latter point that we wanted to be consistent across these markets, and in reality, the rules behind capacity accreditation is different in these markets. And Andrew actually has done work, and we've and some of our other reports where we actually apply the specific rules of those different markets. But for this analysis, we wanted to be consistent, and we wanted to do something that was fairly simple to implement in our optimization. And so that net 100 load hours has been found, at least in the literature that we've looked at and some of which we've performed, to be a fairly good indicator of what the capacity credit will be for a specific resource. But yes, we did not try to implement the specific rules. So I will say in ERCOT, where there is no capacity price, we don't implement any type of capacity value. So that was just an energy only calculation, because that's the only value that is available for resources in that market. So the capacity accreditation was, or that top net 100 load hour method was only implemented in the other six regions.
Okay. And then there was a question on the degradation penalty. First off, just why choose that $5 per megawatt hour? And it seemed a little high. And was this due to the decay from holding energy for later discharge or something else? And then also, what was the reasoning behind going all the way up to that $25 per megawatt hour in the sensitivity?
Yeah, no, so this is a good question, and it is one that actually we're writing a second report that does a little bit of a deeper dive into some of that cost modeling and degradation modeling that wasn't really the central element of this work. So where those numbers came from is it came from a study that came out in Nature Energy a few years ago, where they looked at the opportunity cost to cycling the battery and calculated the optimal linear penalty. So it came from someone else's work where they calculated that $5 a megawatt hour number. I think, and the reason it doesn't think about kind of holding energy and what type of degradation that will consider, that these penalties are really just about cycling, and the notion that if you ramp your battery up and down, that's going to have a cost on your degradation. So how we calculate that is we have a rainflow, it's called a rainflow algorithm, counting algorithm, where we actually follow the state of charge that results from our optimization. And we count how many cycles happen, and we convert that cycle count into a degradation amount using some degradation curves from the literature. But again, there's a lot of detail kind of behind that. I don't really have time to really go too much into that. Do encourage you to stay abreast to our work. But the last thing I'll say is that the reason I didn't show that sensitivity here is because actually going from the $5 to the $25 degradation penalty didn't actually affect our results that much. And the intuition behind that is the storage assets are really deriving most of their value from large arbitrage opportunities. So, by changing from 5 to 25, you're restricting, some arbitrage opportunities in the $5 to $10 per megawatt hour range. But we find that actually doesn't drive the results that much, because this value is really driven by wild or larger swings.
Great. We have a couple more that are on some of the methods, but I think it's helpful to turn to some of the ones that are kind of more discussion of the results. We might come back to those other ones. Just from a big picture perspective, could you again explain why is there a penalty that you've identified for co-locating storage?
Yeah, so it's really good to be clear about this. So the way to think about this penalty and constraint is that wind and solar need a lot of land, and there are certain regions of the U.S. that they prefer to be built in. Think about the Great Plains, think about in Texas, mostly in the West. So they need land and they like access to these resources. But storage has much smaller land requirements, and they can be built basically anywhere. So the idea is that we wanted to find out if there were locations within these markets that had more volatility than wind and solar locations. And so the penalty should be thought about as, let's say I'm a developer and I'm getting this investment tax credit. So it's saving me a bunch of money. So it's like, all right, well, I'm getting this tax credit. I'm just going to put that storage asset at my wind and solar location so that or it's usually solar because I usually take the ITC. So my solar location to get that savings. And so we really wanted to ask, like, well, if you didn't have that cost savings, would you actually want to put that storage resource at a higher volatility node? Because that ITC is really just a federal incentive. It doesn't have necessarily any system value. So we're really interested in this volatility difference. And we did find that wind and solar locations on average are less valuable for storage than some of the highest volatility locations. And so that's how you should think about the penalty, is that these developers choosing potentially to co-locate because of a federal incentive rather than finding a high volatility location. And that's that constraint, and that's the penalty, as it were, as we've defined it.
And then following on that, how would your results change if the standalone storage was eligible for the ITC?
Yeah, so the way I think to think about that, if you think back on let's see if I can go back to the waterfall chart, is you should just think like the results on the left, for the most part, wouldn't change, though you would think that this grid charging, you should think about the sensitivity of allowing grid charging would actually be in place, because there wouldn't be any reason necessarily now to restrict grid charging. So this would be in place, and then this ITC benefit would go away. And so the top level results that I was saying, I think should mostly be in place, is that we will see that there is still a penalty, but that there are construction savings beyond the ITC, which I think you'll get regardless, because these are just balance of system land costs that would be saved. So really, when you look at this chart, just think about this light blue going away, so that developers wouldn't have access to this anymore. and that you would allow grid charging. That's the main way to think about how that relates to our study.
Great. And then at some point, you had a storage value adder that you presented, and the question was just, what are the implications on a storage project or this coupled project economics if you see this like $22 a megawatt hour adder? Is that sufficient to cover the cost of that storage?
Yeah, so this is a good question. This is work that Mark Bollinger actually has done, and if you haven't, I'd encourage you to look at the utility scale solar report, where he'll actually go through the PPAs of a lot of these online hybrid projects to try to extract the cost, the additional cost of storage. And he has found that the storage value adder, or the storage cost adder, I guess now I'll say, for this specific 4-hour duration, 50% battery to generator ratio is around $10 a megawatt hour. So if you compare that to the 22, you see that, okay, that's bankable. There's a lot of value to coupling that even beyond the cost to adding that battery. It's important to point out that that $10 megawatt hour cost that he has found, obviously that incorporates the ITC, so that benefit is taken into account there. But yeah, if you are more interested in kind of some of the PPA cost details, yeah, I encourage you to take a look at this utility scale solar report.
Great. And then just a final question before we wrap up here. Do you have any insights on how these results might look different in a non-ISO or RTO region? And in particular, a large number of the coupled systems that are going to be coming online soon are in the West and outside of the California ISO.
Yeah, so this is a hard question to answer. As we did show that the non-ISO West is also a big location for these projects. Obviously, those regions, the reason we didn't look at them is because they don't have nodal prices. So we actually can't employ the method that we used to answer this question. But they're, even though they don't have nodal markets, it's still a transmission network. So a lot of the conclusions that we saw in California, we think apply pretty strongly to the West as well, given that especially the Southwest has seen pretty dramatic increases in solar. And so you would have to imagine that the utilities that are operating in those areas kind of have started to see the value decline of solar, though they don't see it, from a market revenue standpoint, but from an operational standpoint, they probably do see that. So that definitely, when you think about those other regions, I think what's interesting is to think about at what point will those regions have bigger solar penetration amounts. Because I think we've really seen that in California, that as solar penetration has increased, these coupled projects have become more and more valuable. And California in the West is really where most of the solar gets installed. But as the Southeast increases solar, you might start to see some of these trends too in that non-ISO context. And I think the last point I mentioned here is, it was interesting that wind has increased in Texas, obviously, and in the Midwest or the middle part of the United States, and we didn't tease apart as strong of a relationship between the storage value and the wind penetration. Anyway, that's kind of an aside to your original question, but I do think about these penetrations of renewable energy to apply to these non-ISO regions.
Okay, and thanks so much, Will. We also appreciate everybody for putting in all of your questions, and thank you again for joining. We weren't able to get to all of them, and again, there's a lot of great questions in there. And so what we'll try to do is follow up with some of those remaining questions via email. We'll also post this webinar recording to the location where the report can be found. Again, I'll put that into the chat again so that you can find that at a later point. And we just appreciate everybody coming and joining us, and we hope you all have a good day. Thank you so much.
Yep. Thank you.